Good afternoon to all viewers. My name is Alexandre Giron and I will present the work entitled Bitcoin Blockchain Steganographic Analysis. I'm a professor at Federal University of Technology and a PhD student at Federal University of Santa Catarina in Brazil. The presentation is organized as follows. First, the introduction of this work is presented, followed by related works, main contributions, methodology, followed by results, conclusions, and future work. This work is in the context of steganography and blockchains. Blockchain is a decentralized digital registry protected cryptographically from tampering. Since its beginning with Bitcoin, a variety of electronic services are beginning to explore the benefits of using blockchains in their infrastructure. Blockchains can have a strong integrity, which means that the data cannot be altered once it is registered, and it can have public or permissioned access for participants. These participants, also called nodes, download the data, maintain a local copy, and protect and process data blocks. A consensus algorithm is executed, and so the participants agree on the same state of the blockchain. A problem found in this network is when malicious users or malicious participants insert inappropriate data to the blockchain. For a legitimate user, data insertion may be convenient, for example, for proof of existence services or proof of elapsed time services, among other purposes. Researchers found up to 1,600 files up to 2018 in Bitcoin blockchain. However, if the data inserted is objectionable or inappropriate, it imposes a threat, especially for public blockchains. Every participant must have a local copy of the blockchain, and so this threat may contribute to unauthorized spread of this inappropriate data all over the network. In addition, such data when inserted cannot be deleted. Countermeasures to this threat include content filters, but the difficulty increases when the data hiding techniques are used in the blockchain. Steganography hides that the communication is happening. It camouflages the data that is being used by the participants when they are communicating in a specific channel. Exploring blockchains for steganography has some attracting features. It has free access when public blockchains with a degree of anonymity. It lacks of central authority, and communication is not susceptible to censorship. Data cannot be deleted. Going back to the problem stated previously, what if malicious users hide inappropriate data in the blockchain? Institutions may want to detect and avoid such problem. It seems that Partala was the first to link blockchain with steganography in 2018. Al-Salami and Zhang also explored this topic by analyzing attacks and also the use of steganography for relatively good purposes. Fionov further advanced this line of research, proposing other covert channels for blockchains. However, none of these works searched for evidence of steganography use in real case scenarios. Since Bitcoin is a very popular cryptocurrency, are there any steganographic messages in the Bitcoin blockchain that could be detected with standard stegananalysis? That is the line that we follow in our work. The main contributions of this work are an overview of the available techniques for insertion and hiding in the Bitcoin's blockchain, a search for steganographic evidences in Bitcoin, considering the first 253 gigabytes of blocks of the blockchain, and also lessons learned from the case study. There is no specific proposal found to detect steganography in blockchains, and no steganographic evidence was found by our experiments. But we discuss why we cannot conclude that the blockchain is free of hidden messages. The methodology was designed first over the data insertion methods available in the blockchain. In Coinbase transactions, near to 100 bytes of arbitrary data can be inserted. You viewers can see the well-known example, which is the message contained in the Genesis block in Bitcoin. Another alternative is to use the return opcode, which is the standard way for data insertion since 2014, limited to 83 bytes. Op-return invalidates the outputs of the transaction. Standard transactions can also be used to insert data, substitution of the output address by the data, which results in burning coins. They cannot be further expanded. The types of standard transactions are the following: pay to pub key hash, pay to script hash, or the obsolete pay to pub key. The last mode of insertion is by using non-standard transactions. It is possible, but miners and participants often ignore it since they do not recognize scripts or the type of transaction. On the other hand, a further level is when transactions contain hidden data. Partala's approach hides data in hashes by using the least significant bit of the payment addresses, a hash in this case. The ciphertext of the message is embedded in the LSB. This approach is similar to hash channels by Wu in 2005. It is claimed that if a pseudo-random ciphertext function is used to encrypt the message, it can be hard to detect such embedding. Another possibility is to explore the nonces to hide data. The bitslog.com website has published that the nonces present in Bitcoin have unexpected patterns, instead of looking random. One of the conjectures is that they could contain hidden messages. These two ways of hiding data were explored in our work, but other types can be used. Al-Salami and Zhang discuss how to hide information in digital signatures present in blockchains, and Fionov discuss how the addresses can be arranged in a way that forms a hidden message. Approximately 253 gigabytes were analyzed by our work. 23 chunks of data blocks were created using the timestamp information divided in semesters. This division was performed in order to map possible findings with the time that it was inserted in the blockchain. 2 experiments were performed, highlighted in the slides. Hashes in the transactions were analyzed based on the Partala's approach, and also the nonces were analyzed, since the results of the Bitslog website was restricted to the early blocks of the blockchain from 2009 to 2010. Statistical metrics were computed: arithmetic mean, Shannon's entropy using bits per byte metric, and the monobit test, for instance, compared to a synthetic data set of LSB generated by SHA-256 hashes. So we compare this synthetic data set of SHA-256 LSB data with the results found in the LSB of the transactions. If the results are different from the synthetic data, the chunk would be a candidate to contain steganographic messages. And the last step is to try to recover information in the extracted data using file carving by the Scalpel file carving tool. The results of the first experiment are a set of 23 tables from chunk 1 to chunk 23. The data was extracted from the LSB of each type of transaction addresses. The first table on the top of the slide shows the metrics of the first chunk, and the second table on the bottom is from chunk 9 as an example. Less data was extracted from chunk 1 compared to chunk 9. The metrics were computed, and they are not very close to the synthetic data generated with SHA-256 hashes. However, no evidence was found in the data extracted. On the other hand, in chunk 9, the metrics computed are very different from the synthetic dataset. For instance, the monobit test failures reaches 66% in Coinbase transactions, 100% in PubKey, and 86% in pay-to-PubKey extracted data. However, this was not an indicator of steganographic messages. It was later checked that a lot of addresses were repeated among the transactions. Therefore, this metric would not indicate that is indeed a hidden message. Therefore, same addresses have the same LSB, and so the extracted data does not look random as it should. Still, no evidence were found by Scalpel, even by removing the duplicate addresses. The files encountered by Scalpel were checked to be false positives, and all the metrics were computed for all of the 23 chunks. The results of the second experiment is a set of 23 sets of byte histograms. For example, here it is presented the least significant bytes on the top and most significant bytes on the bottom of nonces from chunks 1, 12 and 21. It can be seen that in chunk 1 does not look random. Chunk 1 is from the left of in this slide. Chunk 12 looks closer to random but also has patterns, and chunk 21 also does not look random as expected from a nonce. These results corroborate with the findings of the BitLog website. All of the metrics were computed for all of this extracted data, and also the Scalpel file carving tool were executed, but no concrete evidence has been found in the 23 chunks analyzed in these experiments. Only false positives, which were later checked, and there is no evidence of steganographic evidence in this data using our methodology. The main conclusions of this work relies on lessons learned from this case study in Bitcoin's blockchain. A significant part of the network has been analyzed, as previously mentioned, to 253 gigabytes compared to the near to 300 gigabytes that is the size, near to the size of the Bitcoin blockchain today. Different behaviors were found by the experiments. In the first experiment, the changes can be associated to repeated addresses. So the least significant bit was the same since the same address, since it was the repeated addresses in the transactions. In the second experiment, the changes in the behaviors found, one possible explanation is that the behavior changed after mining pools started to operate in the blockchain. Coordinate miners could iterate through all of the 4 billion possibilities of the nonce without finding the target hash. A consequence of mining pools and later the ASIC hardware for mining is the use of the extra nonce, and therefore the nonce was not the only factor used to find the target hash. A difficulty is that there is no specific approach for steganography in blockchains found in our research, added to the large amount of data processed. And therefore our conclusions is that no evidence has been found with our methodology, but we cannot argue that Bitcoin is free of hidden data. A specific approach would help to protect blockchains from steganographic exploitation. Future works include explore other blockchains and evaluate clustering techniques. So using clustering techniques, we can map interest transactions together and then extract the data from these clusters in order to search for steganographic evidence. The last slides are the references used. That being said, I'm now open to questions and suggestions. Thank you for your attention.